got his PhD from University of Dundee, right, or UK.
Yes.
And his main research area is about the scoring, the scoring combinatorial game theory, right? Now, today he will give us a talk about his recent work about in this field. Okay, let's welcome.
Hi everybody, so today I'm going to talk to you a bit about game theory. So before we get started, the first thing I want to talk about is what a combinatorial game theory actually is. So combinatorial game theory is the study of all two-player perfect information games. So a good example of that would be a game like Weiqi or Xiangqi, where you have two players and they both have complete information about the game. So in other words, they know where all their opponent's pieces are, they know all their opponent's potential moves, they know all their opponent's potential available strategies. So generally we call the two players left and right, and the reason for that's going to become obvious in a few seconds. So generally speaking, with combinatorial game theory, there's two types of ways, or there's two ways that we usually study playing games. The first is called normal play, where we say the last player to move is the winner, and the second is called misère play, where the last player to move is the loser. And mathematically speaking, we write a game like this. So a game position, which we call G, is going to be equal to a pair of sets that we call GL and GR. And GL is going to be the set of moves that left can make from G, and GR is going to be the set of moves that right can make from G. So this is why we call the players left and right, because left's options go in the left-hand bracket, and right's options go in the right-hand bracket. Now, generally speaking, when we study games, basically combinatorial games in general, or the vast majority of them, break down into what we call the disjunctive sum. So what it means is that you have your overall game, but you're actually, in reality, what you're playing are lots of little games all at the same time, because they sort of act independently. So in other words, moving in one component doesn't affect moving in the other component. And we call this the disjunctive sum. And it's written like this. So what it means is, if we're playing the disjunctive sum of two games G and H, then left can move on G or H, but not both. And we also have the negative of a game, which is basically just to swap all the left options for right options. So if we were playing Go, for example, what we would do is we would just swap all the black pieces for white pieces and vice versa. So you're just swapping around all the players' moves, and we call that the negative of a game G. So let's just look at a little example. So a sort of typical combinatorial game that we study is something called domineering. So the rules are like this. First of all, the game is played on a checkerboard with some predetermined shape. So it doesn't have to be square or rectangular, it can be any old shape you like. And players take it in turns to place tiles on the board. So these are usually dominant pieces, that's why it's called domineering. And each tile must cover exactly 2 squares. And left places his tiles vertically, right places his tiles horizontally. And the last player to move is the winner. So to use this notation that I just introduced, the first position might look something like this. So we have a little square board, and on left turn you can either place a piece on the left hand side of the board or the right hand side of the board, and on right turn you can either place a piece on the top of the board or the bottom of the board. And generally we just say that the 2 left options and the 2 right options are equivalent, so we just eliminate the other 2, so in reality it just looks like this. And for the disjunctive sum, it looks a little bit like this. So if we play the disjunctive sum of a square board with a single strip, then on left turn you can either make a move on the square piece, or you can make a move on the vertical strip. And right can only move on the square piece because there are no horizontal strips that are 2 squares long. And the negative of a game would look like this. So if we have a negative of this game, it would just be this. So in other words, we just swap the left options for right options. So when we talk about combinatorial games, we're usually interested in who wins, or rather, who has a winning strategy. And we split these up into 4 what we call outcome classes. So what an outcome class means is that if a player plays his best strategy, then this player could win. It doesn't necessarily mean that he's guaranteed to win, it just means that he has a potential winning strategy if he always makes his best move. So there are 4 outcome classes. The first we call L, which stands for left player win. So this is the set of all games that left can win if he moves first or second. So in other words, left has a winning strategy whether he moves first or second. But it doesn't mean that right can't win if left makes bad moves, for example. And then R is just the same thing, but for right. And then we have a set of P positions, which stands for previous player wins and previous player win, and it means the second player to move has a winning strategy or is the winner. And finally, we have a set of N positions or next player wins, which means it's the set of all games for the first player to move is the winner. And finally, just to sort of give you an idea, so what we're really interested in is comparing games. So if you imagine you're playing a game and you've got a whole set of options and you want to know what is your best possible move. So that's basically what the idea is all about. So this is going to be a little bit technical. I'm not really going into the details of this, but you can just sort of accept this because this is just the kind of standard stuff that I don't really want to get into all the little nitty-gritty details. But generally, for some games we can give them a numerical value. So a game X or an X is a number if all the left options and all the right options, there's no left option that's better than a right option. So greater than or equal to means that if XL is greater than or equal to XR, then that means that the XL option is better for left than the XR option, basically. And as I said, this is going to be a little bit technical, but you don't really need to know this. It's just to kind of give you a little idea. So basically, when we talk about numerical values and comparing games, basically what we have is what we call an identity. So basically the entire outcome class of P positions, so everything that's in the set of P positions is just equal to a game where neither player has an option. And we call this game 0. And the general rule is, without going into any of the details, the general rule is that a game G is greater than or equal to H if G minus H is greater than or equal to 0 in terms. So what that means is if we play G minus H, if left can win moving second on G minus H, then we say that G is better for left than H is, basically, without getting into all the sort of little nitty-gritty details of it all. So what does this mean? So the first thing is there's 2 ways to reduce games. The first is called what we call dominated options. So if we go back to the example I had of the disjunctive sum, where left has 3 options, and we look at 2 of them in particular. So the first one is this, and this particular game has value, we give value 1/-1. And his other option is this, which we give value 2. So what this means is, the first one, what it means is if left moves, then he gets a 1 move advantage. If right moves, then he gets a 1 move advantage. And on the second one, it just means that left has a 2 move advantage over right, basically. So what we get is that the second option is actually bigger than or equal, is better for left than the first one. And so when we're playing the game, because no matter what the situation is, this option here is always better for left than this option is, regardless of the situation. So in other words, we never ever need to think about this particular option when we're analysing this game, because there's no reason why left would choose to play here when he can play here. So we just eliminate it from the option set. So we say that this is a dominated option. So that means we just delete it from this option set. So in other words, this just reduces to this game here. And the second one, which is kind of complicated as well, and I'm just going to give you the definition without actually showing you an example because it is a little bit technical. The second way of reducing games is called reversible options. So if you imagine you've got some game G, and left has some option A, and the right option from A is better for right than the original game G was. Whenever left moves to A, right will immediately move to AR, because he's moving to a better position than the original game was. So when we consider G, rather than doing this particular set of sequence of moves, because whenever left moves to A, right is always just going to move to AR, we don't need to, we can just replace A with the left options of AR. So G just ends up looking like this. So that's reversal options. So the idea of this is that we end up with something called a canonical form. So we say that game G is in canonical form if it has no dominated or reversible options. And for the set of normal play games, we find that normal play games are actually a partially ordered group under the disjunctive sum, which means they're very, very nicely behaved set of games. And the elements of the group are just the canonical forms, and each canonical form of a game is unique. And finally, just to say that none of this actually holds for Misere games. When I say none of it, what I mean is that Misere games are not a nice set of games. So they do have canonical forms, but finding a canonical form for Misere game is a lot harder than a normal play game, basically, without going into all the details. Okay, so next we talk about scoring games. So what we talked about is games where the winner is determined by who moves last. But there's certain games where the winner is determined by some sort of score. So getting back to Wei-Ti, when you play Wei-Ti, you get 1 point every time you capture one of your opponent's stones, or you get 1 point every time you capture a piece of area. And the winner of a game Wei-Ti is the person who has the most points, not who moved last. So in terms of combinatorial games, we want to think about mathematically or intuitively what properties would we like a scoring game to have in general. So the first one is that the rules of the game clearly define what points are and how players can either gain or lose them. So with Wei-Ti, as I just said, you get a point every time you capture one of your opponent's stones, and you get a point every time you capture a piece of area. So we know when we play Wei-Ti or Go, we know exactly what points are. Second thing is that when a game ends, the player with the most points is the winner. So again, this is obviously true for Wei-Ti because you win by having more area or more points than your opponent, not by moving last. The third thing is if we're comparing games, we'd like points to always mean the same thing regardless of which game it is we're talking about. So if we're playing a game in G, then we'd like 1 point in G to be equivalent to 1 point in some other game H, because otherwise it makes it impossible to compare them. So points are points regardless of which game it is we're playing. It's just a standard unit of measuring. And finally, just from the mathematician's point of view, and the reason for this fourth point here, which is that at any stage in game G, the score is going to be the difference between how many points left has and how many points right has. The reason for this is because conventionally on the normal play, when we're talking about games as numbers, positive numbers are games that are good for left, and negative numbers are games that are good for right. So in terms of a scoring play game, just to keep with this convention, we say that positive scores are good for left, and negative scores are good for right. So that's just the intuitive definition, but what about the formal? So just to kind of make this a little bit clearer, I'll just show you diagrammatically. So diagrammatically, what a normal game tree would look like is something like this. So the nodes here represent a position, and the edges represent the moves. So left sloping edges are moves that left can make, and right sloping edges are moves that right can make. So left sloping edges are moves left can make, right sloping edges are moves right can make. Yes. Just make sure I get that right. So with this particular game, left can go to some position here. So left can do this. And then from here, right has no move, but left has another move. And if right goes down here, then left and right both have a move. So that's just what a typical game tree looks like. For scoring games, it's exactly the same, but instead we now put numbers on all the nodes, and the numbers here represent the score associated with that particular position. So when you move to a new position, then naturally you get a new score that we associate with that particular position. So I just numbered this randomly. So mathematically, what does this look like? So mathematically, we define a scoring game rather, to be a set of options for left, a set of options for right. So it's exactly the same as we had before, but the only difference here is that we added this new value, GS, which we call the score. And this is just some real number, and again, it's exactly what I said before, it's just the difference between the number of points left has and the number of points right has at that particular point in the game. So GS is just simply the score associated with the position G. Disjunctive sum looks a little bit different, but it's exactly the same thing. The only difference here is that we're now using two symbols. We're using plus sub L, and we're using just an ordinary plus symbol. So the reason for this is because when you take the disjunctive sum of an ordinary combinatorial game, you're just summing games. But when you sum a scoring game, you're summing the scores as well as the games. So we have to do these two operations separately. So the normal plus symbol here just means plus, as you would normally, as a normal sort of thing that you do, so it's just plus. But this here means disjunctive sum. So that's the reason why we use two different symbols, but it's basically exactly the same definition that we had before. And the negative of a game G is also exactly the same thing, we just swap the left options for the right options. So, the other thing that we need, if you remember when I talked about outcome classes, I said that we're looking at, what we're really interested in is optimal play. So who wins if they play the best strategy. For scoring games, this is slightly different because obviously moving last, as I said, is not relevant anymore. So I defined this new number, which I call GSLF, which means the final score when left moves first. So the idea is that when left plays, he's trying to maximize the score, and when right plays, he's trying to minimize it. So this left final score is simply the maximum possible score that left could achieve if both players were to play the best possible strategies and left moves first. And we have a similar one for right, so we have a GSRF, but instead of being the maximum, it's now the minimum, but it's exactly the same thing. So, the other thing that I do just by convention, if we say if the left and right options are both empty, then I'll just write this game as a number. So I just write a number, and if I just write a number, that just means that neither player has an option. So it's just like this. It just makes it a bit easier to write and a bit easier to read as well. Okay, so moving on. So outcome classes. So to define outcome classes, we have to do it slightly differently. So what I did was I defined these sets, which I call L sub greater than, L sub less than, and L sub equal, and it's just simply the set of all games where the left final score is either greater than 0, less than 0, or equal to 0. And naturally you get the same thing, but for right. And we also define this L greater than or equal to, which is exactly what you'd expect it to be, and L less than or equal to, which is also exactly what you'd expect it to be, and similarly for right. So when we get the outcome classes are going to look a little bit different to what we had before. So we have this set L, which I call, well, I just call it set L, but it's not really left wins anymore. What it means is that if left has a winning strategy moving first, then he doesn't lose moving second. So he might win moving second. If he wins moving first, he might win moving second, but he doesn't lose moving second. And similarly, if he wins moving second, then he doesn't lose moving first. And we have a similar thing for right. And an end position is exactly the same. This just means it's the first third move is the winner. And a P position is also exactly the same. So that's the reason why I chose the outcome classes this way, is so that the end positions and P positions mean exactly the same as they do for the normal and zero play games. And finally, we have this new outcome class, which I call T, which means that both players tie if they move first. And this obviously doesn't exist in normal and zero play because you always have a winner. So let's just look at an example. So this is a game that I invented, and I actually published a paper about this recently called Pirates and Treasure. And this was just to kind of use it as an example of score and play combinatorial game theory and how we can use score and play combinatorial game theory to actually analyze an actual game. So the rules are as follows. So the first thing is the game is played on some finite simple graph, which is just defined arbitrarily. And left has n ships and right has n ships. And the reason why I call it Pirates and Treasure is because you imagine the nodes are like treasure islands, and the players are sailing between the treasure islands trying to gather up as much treasure as they possibly can. So the idea is that whoever gets the most treasure is the winner. So each ship has some predefined starting vertex, and every node gets a number to indicate how much treasure there is at that particular node. And so on a player's turn, he moves to some adjacent unvisited vertex, and when he does that, he gets all the treasure at that particular vertex. And a player cannot move to a previously visited vertex. And so the game ends when it's the player's turn, and he's not adjacent to any unvisited vertices. And obviously the player that gets the most treasure is the winner. So just to show an example of that, if we imagine we've got this position here, so these numbers in brackets represent the score at this particular point in the game. So if left goes first, then he can move up here and he gets a single point, and then right goes and he gets the 2 points from this node, so the score changes from 1 to -1. And just to show you what this game position actually looks like using our notation, it looks like this. So left makes this move, if left makes this move again, then he gets 3 points instead of just 1. And if right moves, then he gets -1. And obviously we have the same thing for right. So just using our notation, that's what this position would actually look like. And the final scores of this game are -1. So playing optimally, the final score for both players would be -1. And notice the other thing is that this score, the final score, or the winner, is not at all related to who moves last. So if left moves first, right moves last, and right wins. But if right moves first, left will move last, but right still wins. So the winner is not determined by who moves last in this game. So let's look at a few of the properties of scoring games. So here we have the definition of what I mean by better than. This definition is an analog to the definition for normal play games, although it might not be that obvious when you read it. Basically what it means is that G is better for, or G is greater than or equal to H if left can always do better playing on G plus X as you can playing on H plus X for all games X. That's basically what that says. So this definition is analog to the definition for normal play games, although it's probably not so obvious. But the definition, basically one of the definitions for normal play games is that we say G is greater than or equal to H if left wins H plus X, implies that left wins G plus X for all games X. But for scoring games, because it's not just who wins, it's also we can also have ties. We have to change the definition to look like this. So the two definitions are the analog of each other. So the first thing is that scoring games are actually partially ordered using this definition. So I'm not going to go into that, but the first theorem that we had is that for any three outcome classes, x, y, and z, there's a game of g and x, h and y, such that the disjunctive sum of g and h is in z. This means that scoring games are actually pretty nasty. The reason why is that, in particular, if G was an L position and H is an L position, then we could have the disjunctive sum of G and H be an R position, which is really nasty. So what it means is you've got some game G where left has a very big advantage, another game, H, where left also has a very big advantage, but when you play them together, now right has a very big advantage. To kind of put that in context, it's a bit like saying a positive number plus a positive number is a negative number. It's just it's very, very nasty. And the other thing is that, so if you remember before, I explained that for normal play games, the identity set is the entire outcome class, so the entire outcome class of P positions. So for normal play games, every P position is equal to the 0 game, so the game when neither player has an option. For scoring play games, that's not true, and it's also not true for Misere games. So this theorem is actually also true for Misere games, which means that the only game which is in our outcome class, the only game which is in our identity set for scoring games is the trivial game. So in other words, the game where neither player has an option, and the game is a tied score, which is again purely nasty. But domination and reversibility just work exactly the same as they do for normal play. So if G is greater than or equal to H, so we delete dominated options, reverse reversible options, and we can get to a canonical form. But the canonical forms are just a little bit different. And the reason why they're a little bit different is the following reason. Basically, so as I said before, for normal play games, canonical forms are unique. But the scoring play games, you might have something like this. So you've got the game 3/2/1 is equal to the game 3/0/1. So both these games are in canonical form, but you'll notice that they're not identical because the GS value is different for both games. So what it means is that we don't get an exactly unique canonical form. We get something that's very close to being a unique canonical form, but they're not quite unique. But the difference is kind of, as far as the disjunctive sum is concerned, this difference is basically inconsequential. So, a question we could ask is the following, and this was a question that was posed to me by a person, by somebody, which is how can we embed Conway's games into scoring games? So Conway's games was all the stuff I said at the start about normal play games. So the question is, we want to figure out a way to be able to embed Conway's games into scoring games, so we have this kind of complete theory for combinatorial games. So this is the naive approach to this. So if we have the following definition. So here SCG means Conway's games, FSG means scoring games, which I just talked about, and we have this mapping which looks a bit complicated, and I won't get into the details, but it basically means that you map 0 to 0. So yeah, it's kind of a little bit complicated. You don't really need to know what it means, but basically this mapping doesn't work. And the reason why it doesn't work is the following. The Conway game, which we call 1, would map to this game, 0/0/empty set. But under scoring games, this is not true. So for normal play games, 1 is greater than or equal to is greater than 0. So 1 is better than 0. But for scoring games, that's not true. So this mapping doesn't really work. So the question is there a way to resolve this particular problem? Is there a way to answer this question? And the answer is yes. So let's take another look at Pirates and Treasures, just as an example of this. So what I did in my paper on Pirates and Treasures, the first thing I did was looked at the general structure of this game on its own. So you find some set, which I just call the set of all games which represent some position of Pirates and Treasure. And then we look at a subset of that. So what we do for a subset of that, we just instead of making all the nodes some random number, we now change the numbers to be some positive number x. So for example, it could be 1 or 2. But the point is they all have the same value. Every node on the graph, on the game graph now has the same value, which is some positive number. So the question is, if we look at a position like this and ask, is this 1/2? So 1/2, what does that mean? So under normal play, so if we were playing this position but under normal play rules, so in other words we ignore the scores and we're just saying the last player to move is the winner, then this game has value this. So it's -1 0/0, which is just -1 is the dominated option, so it's just 0/1, which is equal to 1/2. We call that 1/2. And the thing is that you notice the winning strategy under normal play is exactly the same as the optimal strategy under scoring play. So what that means is that under normal play, left's winning move is just to take his left piece and move up here, because then right can't move, so left wins. Under scoring play, it's exactly the same. Left moves up here and gets X points, and right can't move, so left wins by X points. So, so the best strategy under normal play is identical to the best strategy under scoring play. So if we look at this, so as I said before, any game with any P position is equal to 0. In particular, if you have two games G and H, and G minus H is equal to 0, then that means G is equal to H. So, in other words, what that means is, under normal play, if we have two of these, and we have one of these, then this is equal to 0, and this is equal to -1, which means two of these would be equal to +1. So in other words, each one of these is indeed equal to 1/2. And one of the things I proved was that the set PT sub x is actually a group. And not only is it a group, but the set of all t positions is actually the identity for this particular group. And so in other words, if we just restrict our set of scoring games to the set PTX, then this is also equal to this, which means that this, two of these is equal to these. So this kind of validates the question, could we give this position here value 1/2? So, as I just said, on the normal play, a half plus a half minus 1 is a P position, which means it's equal to 0. And so what we find is that this works in exactly the same way for Pirates and Treasures when we can just label all nodes with some value x greater than 0. So what if we look at scoring games in general? So the first thing I did again was to look at a slightly more naive approach, and this is in a new paper I just wrote. So what I said was, well, let's look at a kind of what you might expect a set of normal play, or sorry, a set of scoring games which have the appearance of normal play to look like. So we just define some set to be the set of all games where the score is greater than or equal to 0 whenever left moves last, and it's less than or equal to 0 whenever right moves last. So in other words, moving last is always your best strategy. So what does this set look like? Well, it's a monoid, but the problem is it's not a group. And the reason why it's not a group is because they have identity, they have inverses, but this set is not closed. So in other words, you can have two team games, and then when you play the disjunct of sum, you get a game which is no longer team. So this can't really work as an embedding for combi games. So the next thing I did was, well, I said, okay, so for Pirates and Treasures, the basic property that the set PT sub x had was that every time a player moves, he gets exactly x points. So if we look at this more generally, we just define some set of games G such that whenever a player moves, he gains exactly x points. What does this look like? So the first thing to look at is what we call the outcome class table. Now this might not mean very much to those who are not familiar with combinatorial game theories, but basically this outcome class table looks exactly the same as the outcome class table for normal play games. The only difference is that we've replaced the set of P positions with the set of T positions. And the third thing to note as well is that this set is indeed a group under the disjunctive sum. So it seems to look a lot like normal play games. So what I did was we just defined this mapping. So this mapping is very simple. So if you remember, what I defined GL and GR to be was not the actual left options, because the actual left options is GL plus some score X. So we just take our GL, we just map GL to GL and GR to GR. And what we end up with is we can actually prove that the set Team X is exactly the set of normal play games. So the way we did that was with a few little theorems which I'm not going to prove. So the first thing is that we want to prove that this is a bijection. So that means that it's one-to-one and onto. So the first thing we prove is that nothing maps, so every element from Team X maps to exactly one element of exactly one normal play game. So that's what this theorem basically just says. The other thing is that it's a linear mapping, which means that the disjunctive sum of two games G and X is equal to the disjunctive sum under normal play as well. So if we take f of the disjunctive sum of two games G and X, then that's the same as just taking the disjunctive sum of the individual games mapped to normal play. And finally, that it's order preserving. So this greater than or equal to sub x just means that we use exactly the same definition for greater than or equal to that I had before, but we just restrict the set of the games that we're looking at to games within Team X. So we just ignore all the other score and play games. But it's basically exactly the same. So what about misère games? So the question is, we can do this for normal play, but can we also do this for misère play games as well? And it's like, yes. And we use the following definition, which is exactly the same, except now instead of gaining X points when you move, you lose X points every time you move. I'm just going through exactly the same process, so we just define this mapping, which is called B instead of F. And just going through exactly the same thing that I just did, you actually find that you can show that this set, Team sub minus X, is actually identical to the set of misère play games. And so this is pretty cool. So the question is how we can actually use this. So just show you a little example of a game. So this is something I just sort of discovered, and I just kind of added it into my talk at the last minute. So this definition looks a little bit complicated. Basically, the game NIM is just you play on heaps of beans, and on your turn you take so many beans from any one heap. And under normal play games, the last player moves to the winner, and misère play games, the last player moves to the loser. And octal games are effectively the same thing, but we just define the rules a little differently to determine how you actually remove the beans from particular heaps and what you do. Once you remove certain beans from certain heaps. You don't really need to know this definition too much, but basically the idea is that the reason why I'm sort of interested in this particular game is because it's sort of a kind of standard, what we call an impartial game. So, for example, just as an example, this game here, 1, 2, 3, just to kind of show you how this game is played. Under this definition, what this means is, if you take one beam, you can take one beam only if there's a heap of size 1, and you get exactly 1 point for taking one beam. So if there's a heap of size 2, you can't take a beam, you can't take one beam. So when you take one beam, you have to leave a heap of size 0. You can take 2 beams only if there's a heap of size greater than 2. And when you take 2 beams, you get 2 points. And you can take 3 beams whenever possible. So in other words, if there's a heap of beams greater than 3, then you can always take 3. And you get 3 points. So that's just what that means. It's just, so this is just the kind of rules determining how you take beams from particular heaps. So what happened was, under normal play, we got this kind of very, very nice theory that we call Sprague-Grundy theory, which allowed us to solve all these games under normal play. And that was very nice. And I tried to sort of look at this under scoring play games. And the way I did it was to define this function, which basically says it's just it's to kind of cut a long story short, because the whole definition is actually kind of long. This function is basically just the maximum difference between the number of points you can get and all the previously computed values. So we just compute, this is a recursive function, so we just recursively work out what all the values are. And it's essentially like, kind of similar to the Sprague-Grundy function, but it's obviously a bit different. So the first thing is that this function actually tells us the information we want, namely the final scores of a game. And the thing that's kind of interesting about this is what I was getting back to, which is that if you have some octal game and you can only gain X points whenever you move, then what we've just shown is that this is actually just a normal play octal game. And in particular, if you lose X points every time you move, then this is a misère play octal game. And there is a lot of nice theory for both misère and normal play octal games, but what I've actually shown is that, in fact, you can actually, in theory, you could actually use scoring play theory to solve both normal play and misère play octal games at the same time, which I think is really cool. And so the idea is that I had this conjecture. So if you were able to prove this particular conjecture, which namely that this function is always eventually periodic, regardless of what the game is that you're actually playing, then you would effectively have solved all normal play and all misère play games simultaneously, which I think is really cool. So this conjecture is actually really, really important. It's actually, I had this conjecture in my PhD thesis, but until recently I didn't actually realize just how that it's actually a much bigger deal than I actually realized. So that's what I mean. So proof would actually be the solution to not only scoring games, but also misère and normal play octal games all at the same time, which I think is really cool. And there's actually a lot of evidence to support this, that this conjecture is actually true. So I have actually looked at lots and lots of examples that support that this conjecture actually does hold as well. But obviously we're mathematicians, so we need a proof. So the other thing is that, and another thing this is kind of stuff is what I'm sort of looking at right now. This isn't actually written papers yet, this is just kind of my ideas at the moment. So the question is, would this actually work for games if we added loops? So a loop just means that the game tree now has a cycle on it, basically. So would this work for games with loops? So the answer is yes, it would. So if you added loops into the set TMX, you still get loopy normal play combinatorial into it as well. So everything we've done would also work if you allowed set TMX to have loops in it, which is really cool. So what can we conclude from what I've just talked about? So the first thing is that I just introduced this brand new theory which allows us to analyze games that have scores. And I've actually shown that it is actually mathematically possible, that basically Conway's games, the Conway's definitions for games is actually just a special case of scoring play combinatorial game theory. So in other words, my theory is just simply a much more general idea than Conway's stuff. So that's what I've shown in this talk. Although I didn't do any proofs, I actually left all the proofs out kind of deliberately because I didn't want to bore people basically with that stuff. So the other thing, so basically what it means is that all combinatorial games, all of them, can be analysed using score and play combinatorial game theory, which I think is really cool. So I basically devised a complete theory for all combinatorial games, which I think is really cool. So yeah, so thank you for listening, and does anyone have any questions?
Okay. Do you have any question?
No any questions?
Actually, your survey, Combinatorial game survey, was really interesting. What's interested in whether your theory can be applied to some specific game theory, such as Weiqi or.
Oh yeah, absolutely. It's just Weiqi is quite complicated because it doesn't. So Weiqi does not actually belong to the set team X, which means you can't use non-play theory on it. But yeah, and potentially you could. I mean, you could look at some special cases of Weiqi, because Weiqi. The problem with Weiqi, or the game like Weiqi, is that it's what we call exponential time complete, which means that there is actually no solution to the game. But you could look at it. You could certainly use this theory to analyze some special endgame positions or some much more simplified positions. But in general, this game is actually kind of impossible to solve, basically. But yes, you could certainly, you could definitely apply it to Weiqi.
You have shown that Conway's game theory is included in your theory.
Yeah. Yes.
It's a proper subset of your theory, or
It's a proper subset, yeah. And so my theory is much more general.
it's really cool.
Yes.
No question. Send the speaker.
Thank you.